have learned the free electron theory of metals in two ways. One is classical, which was proposed by Drude, and the other one, quantum, which was proposed by Sommerfeld. So for the Drude model, what you had was you have your solid and the solid is considered to have electrons which are moving freely inside. At that time, the concept of this nucleus was not there, positive charges was not there. So in order to compensate for the negative charges of the electrons, he proposed that there are positive charges randomly distributed inside the solid. And then any electron which is there, it will move in a straight line, and then it will get scattered from one of the ions. And this acts as a classical free electron gas, classical free electron gas. And the kinetic theory of gases is applicable here. So he applied that kinetic theory of gases and Maxwell-Boltzmann statistics. Certainly, this was successful in explaining some of the things, electrical conductivity, thermal conductivity, and this Lorentz number. This could explain, but there had been failures, like it was not able to explain the behavior, experimental behavior of the electronic heat capacity of metals, the Hall effect, magnetism, etc. So then arrived the quantum mechanics, and then Sommerfeld augmented his ideas in 1927, and he once again assumed the electrons to be inside the solid like earlier. But for the simplicity, he did not consider the presence of nuclei. He considered as if the electrons are free, all the electrons are free. And according to that model, the valence electrons of the elements constituting the solid, they became the conduction electrons, and they participated in all different kinds of things and gave rise to different properties of solids. So the electrons here, they were free to move inside the box everywhere. So this was modeled mechanically as a potential where you have infinite potential on the surface and zero potential in between. So U equal to 0 inside and outside the potential was infinity. And this was able to explain the behavior of the electronic specific heat, the behavior of. So there was some problem with the Lorentz number. This also was it was explained by this model. Then you had paramagnetism of electrons, which was explained, and also was explained thermionic emission, etc. These were explained. While there had been failures. So, for example, so one of the failures was the observation of positive Hall coefficients, positive Hall coefficients in some of the metals, and this was not understandable. What was another thing which was not understandable was distinction between metals, semiconductors, and insulators. This also could not account for the observed resistivity behavior at low temperatures. It could not describe the superconductivity, could not explain the superconductivity, etc. So what you need is a refinement given to this quantum mechanical model. Am I audible properly?
Yes, sir, you are audible. Only thing is that like because voice comes fast and the what you are writing is a bit lagging behind. So you may give a gap between gap of let's say 1 second or 2 seconds between two sentences, so that whatever you are speaking, it takes generally 1 to 2 seconds. Same thing to be
Okay.
displayed at the participant side. So otherwise, it's perfect, sir. It's okay.
So what is sounding? Hello, hello, hello. Am I
Yes, sir.
audible?
Yes, sir. Yes, you are audible, sir. You are audible.
Yeah, there was some problem somewhere.
No, I think it's perfectly okay. Just you may share again your whiteboard.
The sharing has.
No, sharing has gone. Sharing has disappeared.
Okay, I'm doing.
Sir, it seems there are some connectivity issues at your end because voice is sometimes coming clearly, but sometimes your voice is intermittent.
So I want
Sir, your voice is not audible. Professor Sanjeev Kumar Srivastav, can you hear me? It seems उनके end पे कुछ connectivity issue है. ये हो गया तुम्हारा इसका काम? Professor Sanjeev Kumar Srivastav, can you hear me? Participants, it seems there is some issue at the end of the speaker. Please wait for some time. He is trying to connect again. Professor Sanjeev Kumar Srivastav, can you hear me? Participants, can you hear me? Please write yes in the chat window if you can hear me. Okay, thank you. Thank you. Thank you, participants. Thank you. Yes. So please wait for some time. Professor Sanjeev Srivastava would be joining soon. उनका मोबाइल नंबर है कौन? व्हाट्सएप भी नहीं है उनका। Professor Sanjeev Kumar Srivastava, can you hear me?
Yeah, I am so sorry. There is some network problem here. Hello.
No issue, sir. Now it's clearly audible. Now voice is much better, I think.
Okay. So there was some problem. Some ringing was coming, and then it was going away.
Okay.
Now let me try.
Yes, now it's okay. Actually, I forgot my mobile also on at my home. I thought you
I had
had
been calling you.
I forgot mobile at home only.
No
So
problem.
my students were trying to find out your number from your website. They got one number on the website, but that number is not working.
Okay.
So participants, Professor Srivastava is again back. There was some issue, the connectivity issue. Now he is again continuing his lecture. Over to you, Professor Sanjeev Srivastava.
Yes, sure. I am just starting.
Okay.
So I have to be slower also. So there had to be refinements on the Sommerfeld model. Uh, Before we go for the actual refinement, I would like to remind you of some important features of the quantum free electron theory given by Sommerfeld. So, just very important features. And you start with a box or sample of length L, cube of length L, where u is equal to 0 inside, and on the surface you have u equal to infinity, as was discussed earlier, which is equivalent to your particle in a box problem. So infinity here, and this box length is L, the particle energy is E, and since u equal to 0 inside, you have to solve the Schrodinger equation minus h cross square by 2m del square psi equal to E psi. And this here there is so this leads to the wave function, which is three dimensional. This is equal to 1 by root v, where v is the volume of the solid, which is equal to LQ. So I am doing this just because there might be a difference in notations from the earlier lectures. So you just note down the differences. And e raised to the power I k dot r. You have boundary conditions, which are periodic boundary conditions. The wave function at the boundary, y is z, at other boundary is the same as at the previous boundary. So psi x plus L y z equal to psi x y z, etc. So here you have kx equal to 2 pi by L nx, ky equal to 2 pi by L ny, and kz equal to 2 pi by L nz, where nx, ny, and nz, they are all integers. And after solving this, one important quantity which you had got was the energy as a function of k, which was h cross square k by 2n. This is one of the most important things which the theory of solids gives you. This you can say for the free electron model, this you can say that this is dispersion relation. And you must have noticed that this dispersion relation graphically, it will be a parabola of this kind. So here you have E and here you have K. And if you put K in the units of 2 by L, you will have 0 here, 1 here, 2 here, 3 here, and so on, minus 1 here, minus 2 here, minus 3 here, and so on. So for each of them, you will have 1 point on the parabola. For 1, you have this point, for 2, you have this point, and for minus 3, you have this point. So you have all these points on the parabola. Actually, they appear to be very discrete, but we have to consider that this L is very large. This L is very large, which is almost greater than 10 raised to the power 8 atomic lengths. So basically what you have, if you draw your parabola not as a function of So not K written as 2 pi by L, but 2 pi by A, where A is lattice constant. And you have 0 here, 2 pi by A here, and minus 1 here. Then what you will have is you will have around 10 raised to the power 8 points on this parabola between 0 and 1 itself. So this parabola, this becomes continuous for a, a measurable solid. So this is continuous. This parabola is very important. And here delta k, so the points will be so close. There will be 10 raised to the power 8 such points here that the distance between 2k points is almost 0. So delta k tends to 0. Then you must have also, so this is one thing. So which one is the important thing? The important thing is E as a function of k equal to h cross square, k square by 2m. Apart from this, what you have learned is there is something known as density of states. Density of states. Density of states, n as a function of E, will be given by V by pi square h cross q 2 mq e raised to the power r. So what you have is this density of states, Ne is proportional to e raised to the power half. This is for KD. So this density of states, let me write it once again, density of electron states. This graphically will be represented by a parabola of this kind. This is in 3D. If you do it, okay, but this is not only the case. Apart from this, you have to consider the Pauli exclusion principle. That any single state cannot have more than 2 electrons. One of them is spin up and another is spin down. So this is density of states. Let me complete this. This is E. So for any particular E, the density of states is Ne. And the number of states between E and E plus DE will be given by this area. Will be given by this area.
Sir, your screen is not visible.
Now,
Just now. Now it's sharing.
it's sharing.
Yes.
Okay,
It's
let me
black,
try.
sir. No, it's fine, sir.
Now
It's fine now.
Yes, sir.
it's visible now.
Okay. So you have these many number of states. You have these many number of states, and each state carries 2 electrons. So you start filling the electrons from 0 energy, and whatever number of electrons you have for your particular material, you keep on filling and you will keep on going like this, and you will stop at one place. You will stop at one place. This is known as Fermi energy. So you have all the states before this Fermi energy. This will be filled, and all the other states, all the higher energies, they will remain empty. But this is true for the temperature T equal to 0. If you have finite temperature, or T greater than 0, then the density of state, the total number of occupied states, so the total number of occupied states, this will be given by, this is equal to 0 to infinity, the density of states, which has to be multiplied by the Fermi function FET and DE. This FET, the Fermi function FET, is given by 1 by e raised to the power e minus some chemical potential mu by kBT plus 1. And it goes something like this. You have F here, and you have, the Fermi function. So you have E here. So its value is 1. It goes up to the potential, this mu, and this value is 1. This is at T equal to 0. And for higher T, it goes like this. So for T greater than 0. Now, if you multiply this density of states with the Fermi function like this, then your density of states, the actual density of states curve, in E, which is something like this, and it had to stop at EF. Now it will be multiplied by the Fermi function at T greater than 0, and this will now be your density of states. And so this black curve is for T equal to 0, and the red curve is for T greater than 0. So this is the density of states, and you have all the states filled till the Fermi energy. So here, in this case, the states are filled up to here. So now this will change. Okay, so this is the case. So what had been the outcomes? We had already discussed. The outcomes, had been CE was given as 1 by 3 pi square AB square N EF multiplied by 2. Notice here this quantity. What is this NEF? N is the density of states as a function of energy, but calculated at the Fermi energy. So if you have the density of states curve, if you have density of states curve of some random anything, and this is the Fermi energy, then this point, this is the value of NEF. So what you get from the density of states is the value of NEF, which decides one of the properties of the solids, that is the electronic specific heat. So I told you that there is one thing, the very first thing is that the dispersal relation, the E versus K, E equal to H cross square K square by 2m. And second thing we are noticing is that in other example, for example, if you take chi, that is the magnetic susceptibility. This is given by mu 0 mu b square. Once again, NEF, that is density of states at Fermi energy. So density of states becomes very important in deciding different properties of different kinds of properties of a solid. So even thermal conductivity, K, which is given by 1 by 3 CE, and velocity, and then some lambda, this also has inside the density of states at Fermi energy. So there are two things important. Two important things. First is E versus K, and second is the density of states. And any theory for solids, it may be metals like the free electron theory, or it could be semiconductors, insulators, or any kind of materials. If you are able to calculate E versus K and E as a function of K and N as a function of E, you in principle would be able to calculate all the properties of the solids. Now, coming to our problem, where now we have to go from the free electron theory given by Sommerfeld to nearly free electron theory. Nearly free. And this considers the periodic potential of the ions which are there on the lattice. The potential is something like this. If you have a solid which has a surface somewhere here, then if an atom is sitting at this point, then the potential will be minimum at the atom and maximum away from the atom. And it goes something like this. Sorry. So one of the potentials is this, for example. Another potential is this. So all these, they fall at the position of the atoms level. So the value of the potential is very large at the surface because the electrons cannot go out.
Sir, again your screen sharing is stopped.
Professor Sanjeev Kumar Srivastava, your screen is not visible. The sharing has lost.
And
Yes, now it is visible.
yeah, I don't know what is the problem. So you have positive charges here, 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 and so. So this is the kind of periodic potential where the periodicity of the potential is the periodicity of the lattice. So this lattice periodicity is equal to A. So then we have to solve. So this potential, the periodic potential, then is of the form U equal to U0 plus U1 cos of 2 pi x by A. So remember this. So U equal to some U0 plus U1 cos some function of x. U1 cos 2 pi x by. Now consider once again the solution of this. So the solution of this, the Schrodinger equation, considering this kind of potential for the free electron when the potential was zero, it was psi equal to some constant into e raised to the power ikx. So for free electron, psi was some constant e raised to the power ikx or ik dot r. So this I am talking about one dimension. So this was psi a e raised to the power ikx. So here also we will expect wave functions of this kind little modified. Now consider two extremes. Extreme 1. In this extreme, we will take small k limit. When we have small k, which is equal to 2 pi by lambda, this implies lambda will be large. Then once again, let us draw the potential. This is your potential U. And then the wave also has the same periodicity. The wave also has the same periodicity. Sorry. When lambda is large, the wave will be like this. Now, the wavelength is very large. When wave is like this, for this large wave, for this large wavelength, these periodic structures will not be visible. So they will smoothen out. So for k equal to small, so for small k, the effective potential it will be once again something like this. And then you have another. And you have infinity here, large value of u on the surface, large value of u. So, and it is constant inside, which you can take as zero. And once again, this is equivalent to free electron. So when you have small k in the E versus k curve, when you have small values of k, you still will have the parabola for small k values. But so there is another extreme where you have k equal to so another extreme. So let me write extreme 2, which corresponds to Bragg's diffraction. What is Bragg diffraction? You have different atomic layers, and then there are X-rays. These X-rays, they get scattered at some angle, and you collect all those scattered light at or X-rays at one angle, and this gives rise to X-ray diffraction. If this angle is theta, then you have 2d sine theta equal to m lambda. That is the Bragg's diffraction condition. Another condition, another way to write the Bragg diffraction condition is k plus g whole square equal to k square, where g is a reciprocal lattice vector. Or this is equivalent to writing k equal to plus minus half g, which is equal to plus minus p pi by a. This is another extreme. Another extreme is k equal to plus minus p pi by a. So if p is equal to 1, k equal to pi by a, and you have periodicity which is matching with almost matching with the lattice periodicity, and if you have this periodicity, there will be reflections. So if you have k equal to plus minus p by a, there will be a reflections. So when we talk once again about E versus K curve, and we are at small values of K, you will have the parabola. But when we have K equal to P pi by A, like pi by A or pi by A here, 2 pi by A, etc., minus pi by A, then something else will happen. So here it will be parabolic, but here there will be something else which will happen. So shall I stop here?
We can take a break here, sir, if possible.
Yeah, I can stop because it is continuous. So I can
Yes.
stop between.
So I think there is yet the candidates have one or two. Let me check whether candidates have written any questions so far. One question is written by one candidate, Prahlada Rao BB. When the question is, extreme 1 and 2, talking about a small k could not make the difference. Question is not very clear.
Yeah, I could understand the question, and this is very genuine question. Very genuine question. So the answer lies here. So when we talked about E versus K, right? And K was equal to 2 pi by L and 4 pi by L and so on. In this case, the value of K was very, very small. And you had the parabola for the guidance, and you had the point here and like that. This L is of the order of 10 raised to the power 8a. Now, if you talk about EA, to so I said that it is because you have 10 raised to the power 8 points, 0 to 2 pi by a. This is fine. When I am talking about k coming to 0, I am talking in reference of a u which is having a periodicity equal to a. When we convert it to E versus K diagram, we have to talk about this 2 pi by a. So in case of 2 pi by a, when we have small k values, k tending to 0, right? So k small means k really small, maybe 2 pi by L or maybe 100 pi by L or so. But when we are close to 2 pi by A, this boundary, when we are here, you have 10 raised to the power 8 pi by L. So there is a difference between this and this. So these two extremes are actually different. Is it okay?
Yes, participant is writing it's okay.
Okay. Any other question? Otherwise, I will continue.
Yeah, participants, if you have any question, you can write in the chat window and you can drop the message here. And meanwhile, we can take a break of 5 minutes. It's 4 p.m. We can come back at 4:05 here. And then at the last of the second lecture, we will take the questions. Whenever you get any question in your mind, you please drop that question in the chat window and the professor, the concerned speaker will take at the last of the lecture. So, sir, we can take a break of 5 minutes.
I have one thing to say. In the 5 minutes, I will try to change my computer. There is some issue with the network and people are not able to hear me. They are writing.
Yes, that would be better, sir. That would be better.
So in the meantime, I will change the computer.
Okay.
I will check.
Okay. Ankita, can you hear me?
Yes, sir.
So Professor Sanjeev Kumar Srivastava, I think he is changing the system, so he has not joined again. So let us wait for another 2-3 minutes so that he will join and then we will start the lecture.
Okay, sir.
Professor Sanjeev Kumar Srivastava, can you hear me? Participants, speaker is just changing his PC, so it seems it is taking some time. Let us wait for some time. He has already joined. Soon he would be sharing his screen and then we will start the lecture. Please wait for some time. Uh, Professor Srivastava, can you hear me? No.
Yeah, I think today there is sort of problem somehow. Hello?
No issue, sir. No issue. If you are okay, I mean, you have changed your PC, then we can start the lecture.
Yeah, I have changed it, but this network somehow I still have the issue. So let me try. Otherwise, I was just asking whether this two lectures can be postponed later and I can take later, because it was really very difficult for me to concentrate even because of this problem.
Yes, sir. We can like if possible, you can cover today till 5, and then whatever is left, we can cover at some other day. There is no issue at all.
Okay,
But
okay.
yeah, today till 5 we can go ahead with this only, and then the remaining part we can take at some other time. I'll give some other slot.
Okay, okay. That would be great actually. So let
Uh,
me try. Huh?
Yes, sir.
There is some problem somewhere. IITs, they don't have this problem, but I am having. Is the screen visible?
Yes, sir. It is visible.
So, okay. Let us go back to the periodic potential, start from here. So we started with this. This was the boundary of the solid. And then you have this periodicity of the potential. So this is your potential. On this side, you can say this is the potential energy. And on this side, it is the position X, where the atoms will be at these places. Now, since this has the potential has the periodicity of the lattice. If the lattice constant in 3D is written as R, no, this is lattice constant in 3D is written as T, and a vector R is a position is a position where, or position of consideration. Then for the 3D case, this potential can be written as U as a function of R equal to U as a function of R plus T. What is T? As I said, that this is the lattice constant, or T is the translational vector in the lattice. So this is given by some MA plus MB plus some other TC, where so this is the T is the translational vector. T is the lattice translation vector. Any lattice translation vector will be written as MA plus MB simply PC, where A, B, C are lattice constants in X, Y, and Z direction, or in their own directions, lattice constants. So the lattice has a periodicity T. So anyway, So whatever lattice translation vector you have, if you add this R in that, then the potential is the same there as the potential at U at R, because the potential has the periodicity of the lattice. So this is the kind of potential which is represented in one dimension by this picture. Now, lattice vector, or you can say this is crystal vector, or whatever this T. So if you have a periodic potential UR equal to UR plus T, then a scientist known as Bloch, he proposed a wave function for this particular potential, which is given by psi as a function of R, and with the index k, this is equal to U with index k as a function of R, and plane wave e raised to the power I k dot R. This is known as Bloch theorem. It tells that if the periodicity of the potential is the same as the periodicity of the lattice, then the wave function will be equal to a plane wave which is e raised to the power I kx or sin kx cos kx, or e raised to the power I k dot r in 3D, multiplied by a function that is periodic in the lattice. This means that now this function ukr will have the periodicity of the lattice. So if you have the function, the potential of this kind, you have the wave function of this kind, which is a multiplication of a plane wave, and a function which has the periodicity of the lattice itself. And this wave function is also known as Bloch function or Bloch wave function. So this is very important theorem given by Bloch, which is used to solve the quantum mechanical problems of periodic structures. Now, once again, let us come back to the periodicity of the potential. So you have the potential which has the periodicity of the lattice. Periodicity of the lattice. Now, in order to solve this solving this quantum mechanically is very complex. So you cannot solve this as such analytically. So Kronig and Penney, they simplified the potential. What did they do? They simplified this potential this way. On the surface, you have potential going to infinity, And inside the solid, the potential has a periodicity. So this is just a simpler replica of the potential which is drawn above. So wherever it is high, this is also high. Wherever it is low, it is zero. This is zero potential here. So you have X, you have X here, and the potential here. Now the periodicity is something like this. So from any point, suppose this is zero, this is at A, and this one is at minus B. So from here to here, this is equal to A plus B. So this is the simplification of this potential. Now we can identify two regions in this potential. The region 1, where you have zero potential, you can see, and the region 2, where you have high potential. Suppose this is equal to U0, this high potential. And this region 1 and region 2, they are repeated. Equations. And we will use, since the potential is time independent Schrodinger equation is used to solve this problem. So time independent Schrodinger equation in region 1, where you had u equal to 0, it will be minus h cross square by 2m. And this Kronig-Penney model is simple one-dimensional model. So instead of del square, you can write t2 psi by tx square. And since u equal to 0, you don't have the potential part here, and this becomes E psi. And this is valid between 0 and A. That is the region 1. And in region 2, where u is equal to u0, the corresponding Schrodinger equation will be minus h cross square by 2m t2 psi by tx square plus u0 psi equal to E psi. So this will be between minus p and. So remember this. This was 0, this was A, and this was minus. This was region 1 and this was region 2. You have U here and you have X here. So we have to solve these two equations. So we can say that this is equation 1 and this is equation 2.
The slides are visible. Screen is visible.
No, sir, it's not visible.
Professor Srivastava, your screen is not visible again.
Yeah. The network went again. So let me tell you.
Mhm. Now it is visible.
Yeah, there is some network problem. So this is the case. Then we will we will assume psi, how the form of the psi would be. Assume psi as suggested by Bloch, because it is a periodic potential. So psi should be in one dimension, u with index k as a function of x, e raised to the power I capital K, not capital K x, where u capital K x equal to small u capital K x plus the periodicity a plus b. So this is what we have in our hand, and the standard procedure is that you take you assume first the form of psi, and then you calculate the psi by dx. Then from here you calculate d2 psi by dx square and put it in the time independent Schrodinger equation. So since I have network problem and we have to manage somehow the things, what we will do, we assume that we have put this form in the Schrodinger equation, two Schrodinger equations which we have written for the two regions, we will put there, and and in the process, we will assume that there is a quantity alpha square, which is given by 2me by h cross square, and beta square equal to 2m by h cross square u0 minus e. This also, if we put in the Schrodinger equation, then the Schrodinger equation, time independent Schrodinger equation becomes d2 psi by dx square plus alpha square psi equal to 0 in the region between 0 to a, and d2 psi by dx square minus beta square psi equal to 0 for the other region. No, so this is 3 and 4, which has been put in 1 and 2. No, uh, so this and this plus the Bloch wave function in time independent Schrodinger equation. If you put in the steps d2u1 by dx square plus 2ik du1 by dx plus alpha square minus k square u1 equal to 0. So in the region 1, and d2u2. So what is u1 and u2? ukx was ukx plus a plus b. So uk in the region 1 is u1, and uk in the region 2 is u2. So the Schrodinger equation converts into this form. du2 by dx minus beta square plus k square u2, this is equal to 0. This is valid for region 2. And as I said, that u1 is uk basically in the region 0, between 0 and a, and u2 is the same uk but between minus b and 0. Now this equation can be considered as equation A, this as equation B. Now our task is so mathematically complex, of course. Then our task would be to solve for u1 and u2. So there are two second order differential equations. And once again, you have to assume the form of u1 and u2. So once again, assume that u1 is equal to some exponential function e raised to the power mx, and then you put it in the equation A, and solve for some steps, and you will get m1 equal to minus ik plus I alpha. This is equal to I times alpha minus k. And similarly, if you take u2 equal to e raised to the power some px, then p is equal to minus ik minus I alpha. This is equal to minus I alpha plus k. And the general solution, this is for u1. Let me remove this. This is still we are talking about this u1. Since A is second order differential equation, it will have two roots that I forgot. Another root will be minus I alpha plus k. And then the general solution will be u1 equal to a e raised to the power m1x plus b e raised to the power m2x, which is equal to a e raised to the power I alpha minus k x plus b e raised to the power minus I alpha plus k x. This is for the u1. Similarly, you get u2 equal to some constant c e raised to the power beta minus ik times x plus d e raised to the power minus beta plus ik times x. So for u1 you had coefficients ab, and for u2 you had coefficients cd. So a, b, c, d, they have some constant coefficients. Now you have an equation for u1 and another equation for u2. Once you have this, you use the boundary conditions. That the wave function u1 at the x equal to 0 boundary will be equal to the wave function u2 at the same boundary, x equal to 0. Similarly, du1 by dx calculated at x equal to 0 will be equal to du2 by dx calculated at x equal to 0. And for the other boundary, u1 at x equal to a will be equal to u2 at x equal to minus b. And so remember this. This is 0, this is a, this is minus b here. So whatever you have here, also you have here. So at this minus b is equivalent to a. So x equal to a and x equal to minus b. They are the same boundaries. Similarly, you will have du2 by dx at x equal to a equal to du2 by dx at x equal to minus b. This will give rise to four equations. And once you have these four equations, I'm just jumping. If you have these four equations, the solution will exist only when the determinant of the coefficients which you get in these four equations, this determinant is equal to 0. And ultimately, if you do the next steps, and this is very long step, you can find this maths in the book Solid State Physics by S.O. Pillai. You can find this book and all the steps are given there. Then what we assume is that this B is very small, but the height U0 multiplied by B, U0 multiplied by B is finite. If you assume this, then you will have beta square minus alpha square by 2 alpha beta. We know the values of alpha and beta. Then beta B sine alpha A plus cos alpha A equal to cos Ka. Then you simplify it further, put m equal to m u0 ab by h cross square. You give the name or symbol P for this. This is also known as scattering power. And the solution will exist. So the solution exists only when you have the earlier condition written in simplified way. P sine alpha A divided by alpha A plus cos of alpha A equal to cos of Ka. See the previous page. Here we have replaced m u0 ab by h cross square as P, and you have solved the determinant, and then you get this. This still is incomplete to visualize. In order to visualize that, we will plot the left-hand side and the right-hand side on the same plot. So how will we do that? On the y-axis, we have the left-hand side, P sine alpha A by alpha plus cos alpha, and on the x-axis, let us have alpha, The alpha A will vary from 0, pi, 2 pi, 3 pi, 4 pi, etc. And the right hand side is cos Ka. So left hand side should be equal to the right hand side. Now the right hand side, since this is a cos function, it can have any value between -1 and +1. This has values between -1 and +1. So what we'll do, we will draw a line for cos Ka. For cos Ka, we'll draw a line which has value +1 here and -1. Now we plot this for t equal to, I think, 3 by 4. If it is plotted, you will have this curve will cut on the pi at the -1, at 2 pi at +1. So you put the value of alpha equal to pi, p sine pi by pi plus cos pi. Sine pi is 0, so p into 0 plus cos pi equal to -1. So this right hand side will be equal to -1, which cuts this cos Ka at the -1 axis. Similarly, if you have alpha equal to 2 pi, you can see this curve cuts cos Ka at +1. So at pi, the curve will cut at -1, at 2 pi at +1, at 3 pi once again at -1, at 4 pi once again at +1, and the curve will look something like this. So it has to cut here, then come up, then cut here, cut here, then cut here, and so on. So this is your p sine alpha A by alpha A plus cos alpha A. Now you can see the value of p sine alpha A plus cos alpha A will be between minus and +1 for this region, or for this region, or for this region. This region, or for this region. You don't have this. This will not be available below this, and it will not be available above this. So what you can say is that between this and pi, you have the solution. So the solution exists here. Similarly, between this and 2 pi, the solution exists here. There is no solution in between. Similarly, you will have a solution here and so on. So since alpha A, if you go back and see the value of alpha, which is assumed, alpha square equal to 2me by h square. So alpha represents the energy. So this is basically the energy axis. So what you can say that the energy which ranges from here to here is allowed, then from here to here it is not allowed. Then from here to here it is allowed, then here it is not allowed. Then from here to here it is allowed. So that way, the energy splits into bands and you have a band structure. So basically, if you plot energy on the y-axis, and this is just some representation, then what you have, you have from the beginning, you have some gap. You didn't have any energy available. Then this is the energy which is available. Then there is a gap. Then there is another set of energies which is available. Then there is a gap. Then there is another set of energies which is available. So these energy levels which are available, these are known as bands. So this is band 1, this is band 2, this is band 3. This is for the nearly free electron model. For the case of free electrons, where you had E versus K as E equal to h cross square K square by 2m, where K was continuous, you had the continuous availability of the energy levels. So energy levels were continuous. So this is corresponding to free electron. And there is another extreme, which we are not discussing here, where although this is solid, but energy levels, they are completely discrete and single values of energies. And this is when it is atomic like, that is, all the electrons are tightly bound. So this is a picture for tightly bound electrons. So what does the Kronig-Penney model say? That the energies available for the electrons are in bands with gaps. So where is the gap? There is a gap here. This is known as band gap. There will be a gap between two consecutive bands. Now, since I had many things to say, but since I am, so this is the Kronig-Penney model. So how it is different from the Drude theory and Sommerfeld? So at least from the Sommerfeld theory, you had this picture, and from Kronig-Penney model, you have this picture. This gives rise to, so this tells that there are bands. Now, if the available electrons are filled till a level which is inside a band, then it is a metal. If it is filled till a level which is just on the top of the band, then there is a gap. So if you have this gap, this particular material will be either semiconductor or an insulator. So the Kronig-Penney model would explain the distinction between metals, semiconductors, and insulators. Very quickly, uh, I will tell you something about the applicability of this. So you have band formation according to the Kronig-Penney model. This is property of semiconductors, which can be used in forms of quantum wells, quantum wires, quantum dots, and the band gaps can be engineered. Band gaps can be changed by changing, for example, the dimensions. So this is 2D, this is 1D, this is 0D. You can change the band gap of the material, and all these can be used. So quantum dots at least can be used in qubits. and photonic devices. And these are the very elementary components of quantum technology. So basically this is the learning the Kronig-Penney model, or whatever you learned so far about the theory of metals. You also learned about the existence of semiconductors and why they exist, and what are the band gaps which give rise to different kinds of materials like quantum wells, not materials, different kinds of structures of materials, quantum wires, quantum dots, which can be used in qubits. Then the E versus K curve, for example, in the band structure, the curvature of the different bands, it talks about, so it gives you the electron effective mass, M star. And if you control this effective mass, then you can generate, or you can make or fabricate quantum Hall effect devices. So once again, these are quantum devices and applicable to quantum technology. And then you produce defects and impurities in semiconductors. These will give rise to defect states in band gap. And these can be used in superconducting qubits. Superconducting qubits. And spintronic devices. So the study of fundamental theories behind the solids, actually it is very important to learn the behavior of the materials which are used for quantum technology. And that way you can design different kinds of materials to use for quantum technology. So I stop here. It is already 5 o'clock. I am sorry that I took long time. Hello.
Thank you, Srivastava. Yes, there has been some issues due to the connectivity, but it was good to have the teaching on the whiteboard, because during the, if we are using whiteboard, candidates get time to understand the things. Unlike the case of PPTs, where if a faculty member is switching PPTs too fastly, then candidates are not able to understand the concepts. So I always prefer to have blackboard or whiteboard more teaching, because candidates get time to understand, to grasp the concept. So there was some issues. So I would try to have one more 1 hour slot for you in the coming days as per your schedule and convenience, so that you can cover what is left.
Sure. So I would be happy to do that.
Yes. So candidates, if you have any question, please write in the chat window. One candidate, Mr. Satyendra Prasad, is writing, yes, it's better to use Blackboard than the PPTs. I think, sir, these questions in the chat windows are visible to you also as a panelist. You can just click on this chat icon at the lower right corner of your system. The bottom at the lower right corner, there is a chat tab, which is where is written CH80 in the WebEx platform. So you can always see the questions written by the participants.
Yeah.
So yes, one candidate is asking there are issues in yes, Canvas is still not working, and it's not like with us in entire country or in globe it's not working. Canvas servers have been hijacked by some persons. Canvas is trying to restore it, but still the problem is not yet fixed. So Canvas is not only with us or not only in India and the globe it's not working. So that's why instead of Canvas, we are using Google Form links and Google Drive links to share you the slides and the link for the recorded lectures. One question is written by Ranjan Tan. He is writing, thank you, sir, for your nice lecture. Sir, I have a question regarding the block function. Is there any form of this block function, as it is very vital to analyze different kinds of solids and their quantum properties?
So the block function has been described. This is conceptually very simple. That if you have a periodicity in the potential in which an electron is there, then its wave function will be equal to multiplication of a plane wave and another kind of function, which is just having the periodicity of the lattice. Now this UKX or UKR, which is equal to UKR plus T. I think your question is here. What will be the form of this UKR, if I am right? So at this point of time, I would just say that this concept that itself gave rise to, gave rise to the solution of the Kronig-Penney model, and there were two things, U1 and U2. They were written for U. And for that particular model, Kronig-Penney model, you must have seen. So if I can go back, So can you see the form of U1?
Yes, it's visible.
So this is one example. Similarly, this U2 is another example. So the form of this UKX, the form of this UKR or UKX will be different in different situations. For the simplest one-dimensional periodic potential, that is a kind of uh, a rectangular kind of potential. For that simplest case, you have seen. But for the actual problems, you will have different kinds of use these wave functions, these block functions.
Yes, any other question? There is one question uh, by the candidate Mr. Sarkar, Partita Sarkar. Sir, just a request, please create a Google Drive link for QT-9 study materials too. We can now no more access the materials due to Canvas issues. If you share the same with your team, we will be, yes. Okay, Mr. Sarkar, I'll give this feedback or this information to our coordinators of QT-9 course. And I understand because Canvas is not working, and due to that, you people are not able to access the course notes as well as the recording links for recorded videos. So I'll be requesting the concerned coordinator for the course QT-09, and then he will be sharing all the notes and the links on this Google Drive as well. So many speakers, many participants are writing, thank you, it was a good lecture.
It was not really because I could not concentrate somehow.
Yeah, but it's due to the connectivity issue. Otherwise, the teaching style is very good because candidates are getting time to understand, to grasp the concept. So, Blackboard teaching is always better than PPTs.
Mm.
And okay, people, a few participants are asking about the marks of the quiz. As I told on Friday also, we will be first completing all three quizzes, quiz 1, quiz 2, quiz 3, and then at the last, we would be telling you the marks of all the three quizzes. We would not be able to tell the marks, separate marks for separate quizzes. We will be telling the marks for all three quizzes in a single go, which will be at the last of the quiz of the quiz 3. And Mr. Satyen Prasad is writing another question. Theory is okay, but can we expect direct simulation method to solve these topic problems? Maybe on any open software or even MATLAB, so we can learn it directly by simulation. What is happening? We can play with it. Actually,
Yeah.
this. Yes,
So
yes,
I
please.
have an answer to this.
Yes, yes, please, please.
Yeah. So actually, the Kronig-Penney model is the very basic, the first step ahead. Then you go beyond this, and then you will learn in the later lectures how more complicated things can be handled. But ultimately, you have to solve the Schrodinger equations for almost infinite number of electrons in a very large amount of potential. So that cannot be handled analytically. Certainly, it can be done only with computers. So there are codes which are existing in order to do these calculations. And this method is called density functional theory. Density functional, density functional theory, or DFT. And there are codes available. Some of them are commercial and some of them are free. One which my students they are using, this is quantum espresso. This quantum espresso is a free software. It works on Linux operating system, and you can get this, you can install this on Linux. You can take help of YouTube videos to do simple calculations or even any complicated calculations of the properties of solids. That was
Yes, Quantum Espresso is a very, very good software, and many people, many faculty members, so those who are working in the in the area of DFT calculations, they are using this. And another is like a Beyond 2K software is also there. People are using Beyond 2K also many times.
Yeah, Wheel 2K I started with, but that is commercial.
That is
So that is commercial. So that's why I talked about it. So
yes.
the other one which you are telling is Wheel 2K. This is commercial. It requires very little amount of money, but this is very extremely good for the precise most calculations. If you really want to calculate the hyperfine magnetic fields in magnetic materials, if you want to calculate the electric field gradient at each atom in a solid, then this Wien 2K is the kind of pure DFT, and this takes a long time to calculate. To start with, I think quantum espresso would be better.
Yes. And participants for doing some general physics calculation or related to condensed matter physics or finding out the properties with the different functions with different values. More general software is COMSOL. COMSOL is a very good software in that manner.
Yes.
It's very versatile. It gives you lots of tools to play with lots of parameters.
Yes.
So it seems there is no further question. So let us thanks again to our speaker, and we will be having one more lecture by Professor Sanjeev sir.